Good afternoon again. Hardly seems like 2 minutes I was last here talking to you about exploring the solar system. And this is Exploring the Solar System Part 2, how we've done it not necessarily by landing robots on other planets, but sending spacecraft out into the solar system. So I'll be talking a little bit about how we get there, how do we actually get a spacecraft to another planet, and what do we do when we get there, and how do we get images back. Now, usually we're interested in scientific data, but for a lot of people, the data is irrelevant. They just want to see images. Data might be taking temperatures and magnetic field measurements and all sorts of other things, but most people are asking the questions, if you're going to visit another planet, show me the photos, show me the images. And again, I'll ask the question at the end, what next? I thought I'd start by just reminding ourselves how many spacecraft we have sent out into the solar system, because I wasn't sure what that number was. We've been doing it for quite a long time, since Sputnik, but the number of spacecraft that have been sent in the last 70 years, when I started adding them all up, I know you can't read this list, but this gives you an idea of just how many spacecraft we've sent. All the way from the very early pioneering spacecraft of decades ago. The most recent one I've got on this list is Europa Clipper, which was sent just a few months ago, launched just a few months ago. In order to get to the nearest planets, so for Mars, for instance, that's not so difficult. If we want to get from the Earth to Mars, because the orbits are not so different, then launching from the Earth and arriving at Mars doesn't take a huge amount of fuel. If we think about the orbit of Mars, this is not to scale, this is just a cartoon, just to give us an idea. If we want to leave the Earth and arrive at Mars, we time it such that the Earth is on one side of the solar system, such that we arrive on Mars when it's at the other side of the solar system. In other words, we follow the blue orbit there, this elliptical orbit as indicated. If I just temporarily take the orbits of Earth and Mars away, you can see the orbit that takes us from Earth to Mars is an elliptical orbit, and basically, as long as we can give our spacecraft a kick with our rocket engine, we will coast all the way from Earth to Mars, and if we miss Mars, we'll coast all the way back again. The catch is, unfortunately, because it'll take us about 1.5 years to do that, if we were to coast to Mars and then coast home, we would arrive back here 1.5 years later, but of course the Earth takes a year to go round the Sun, so the Earth won't be there anymore. This is one of the reasons why going to Mars is a little bit tricky, especially with human missions. Not so bad with robots, they don't mind so much, but humans have a habit of dying if you don't give them enough food, enough water, or enough oxygen. When it comes to going beyond Mars in the solar system, in the 1960s it was established that what you can do is actually use a gravity assist, a slingshot. As you go past one planet, you can use its gravity to accelerate you to visit other parts of the solar system. For instance, you can use the very massive planet Jupiter to give you a slingshot to send you on to Saturn. This was done with Voyager 1 and Voyager 2 back in the 1970s. They were launched in the 70s. So that's Voyager 1 that was given a slingshot past Jupiter and then went on its way to Saturn. Voyager 2 followed shortly behind it, and it was given a slingshot from Jupiter, which sent it onto Saturn, and then by carefully maneuvering it, it got a slingshot from Saturn, which sent it onto Uranus, and then it got a slingshot from Uranus to send it onto Neptune. It didn't need to do a slingshot from Neptune. It was already going plenty fast enough to leave the solar system. In fact, the slingshot actually slowed it down slightly when it went past Neptune as it went over the pole to get the best view possible of the moon Triton. But this is a great way of not only accelerating the spacecraft, which means you get there sooner, which is fantastic, but also you use less fuel because you don't have to have a rocket engine with a whole load of fuel, and you don't have to burn the fuel to fire the engine to get your acceleration. You can use the gravity of the planet. So not only do you get a speed increase for free effectively, with less fuel you can take more scientific equipment with you, or more cameras, or whatever else you want. So it's a win-win situation to use gravity assists to explore the outer solar system, and it can also be used to explore the inner solar system as well. Gravity assists are being used by Bepi Colombo, for instance, to go and visit Mercury, which is what it's currently doing. Here's one of the very early images of a planetary body. Any idea what it is? Yes, very good. It is indeed an early one. This is Luna 3, so the title of the spacecraft tells you what it is. This is the far side of the moon taken in 1959. This, of course, was long before we had digital cameras. So how do you take a picture like this? Well, amazingly, I can just show it with some of the noise reduced, just so you get a better idea. Okay, it's not particularly high resolution, but it was taken in the 1950s. How did they actually get an image like this? It was rather incredible because without digital cameras, what they had to do was expose emulsions, i.e. film. You remember film before digital cameras? They would expose the film, and on board, they didn't bring it back to Earth, on board they developed it, fixed it, and dried it in the chemical sense. Then they took the developed film and ran it past a scanner, a CRT, a cathode ray tube flying spot, was then projected onto the film, and a photomultiplier behind the film would record the intensity variation as the spot scanned over the film. Then that signal from the photomultiplier was transmitted back to Earth, and there they reconstructed the image a bit like a fax machine. You take the intensities of the flying spot of the developed film, send it back to Earth, and like a fax machine, you then generate the image. So a remarkable feat of engineering for the 1950s. And if you compare it with an image that we can now take from, for instance, a NASA Lunar Reconnaissance Orbiter, taken something like 50 years later, you notice that not only can we now do it at much higher resolution, but basically everything was right. All of the intensity variations that were seen in the 1950s were definitely real. There were no really big artifacts. So it shows you just how good the imaging was in 1950s. But nobody wants to have to give a spacecraft an entire developing section in order to take pictures on film and then develop it and fix it and dry it and then scan it. You don't want to have a Max Spielmann lab on board your spacecraft. You want to find a better way of doing it. So in the 1960s, they developed the concept of a digital camera. So for those of you who like digital cameras, for those of you who like the idea of having a digital camera in your phone that you can carry around all the time, the world's first digital camera was on the Mariner spacecraft. Digital photography was developed for spaceflight. And the spin-off is we now all have one, and it costs next to nothing to buy a digital camera. So the digital camera was here for a Mars flyby. The information from the digital camera was recorded on tape. They were really desperately keen on the idea of the tape running and stopping because the tape was effectively on a loop. If the tape recording didn't stop, then it would record all of the pictures of Mars as it flew by. But once it had finished flying by Mars and was just looking at deep space, if that tape didn't stop, it would just keep on recording nothing, 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 and it would wipe over the images of Mars. Luckily, it did start and stop on demand, so the tape did record the images of Mars. Once it had flown past the planet, which only takes an hour or two, then you basically replay the tape and transmit the information back to Earth at your leisure. And that, again, gave us the first digital images of another planet. Again, with modern technology, we can just remove some of the noise and see what's going on. So, not that impressive compared to the superb resolution that we can now get with modern equipment, but again, this is the 1960s when the first digital technology existed. So we've now visited effectively every major body in the solar system and some of the smaller ones as well. So we visited all of the planets and a number of the dwarf planets and a number of the asteroids. Again, I haven't got time to tell you about all of the missions that have been going on, but let me just pick out a couple of interesting ones. Cassini was sent to Saturn back in 2004, and it finished its life by being crashed into Saturn in 2017. Why did we crash it into the planet rather than just leave it orbiting? Well, because we think the moons of Jupiter and the moons of Saturn are quite interesting and could, in principle, harbor life. And we do not want to contaminate those moons by allowing one of our spacecraft to accidentally crash into a moon at some point in the future. So in other words, the spacecraft was deliberately put into a suicide dive into the planet to keep it away from the precious moons. This gives you an idea of the size of a Cassini spacecraft compared to a human in the bottom right corner there. And I'm not going to talk through all the numbers, but this is just NASA's way of summarizing the mission in a whole load of numbers. How many billion miles has it launched? How many gigabytes of data has it collected? How many thousands upon thousands of images did it take during its more than decade lifetime? The one thing I find quite interesting is the number of commands that were received and acted upon. Millions of commands were sent to the spacecraft, usually turn this way and photograph this, and then let's get the data back. So huge amount of information being sent and returned from these missions. If we think about what we can see from Earth, there's an image of Saturn as imaged by the Hubble Space Telescope here on Earth. If we have a look in detail at what's going on in the ring system, we can see some detail from a Hubble image, but it can't possibly compete with the amount of detail we can see from Cassini simply because we are so much closer. And when Cassini arrived at Saturn, it spent a certain amount of time looking at the planet and the moons, and in particular the ring system, to try and understand the dynamics of these trillions of icy particles that are all independently orbiting the planet Saturn. It looks more like a long-playing record when you look at it in detail. Some moons, especially shepherd moons, are actually keeping some of these ice particles in particular orbits, which is why we don't get a completely uniform disk, but this ring system that we see. It is estimated that although the ring system is some 250,000 kilometers or so in diameter, it might only be a thickness of a few meters or a few tens of meters. It is literally the thinnest thing in the solar system. At the right time of year, at an equinox, the sun comes in the ring plane and shines across the rings rather than down onto the rings, and we can then see some interesting shadows that are cast by the sunlight coming in the direction of the arrows there. So although most of the ring system has variations that are only meters or tens of meters, these bumps here, casting these long mountainous shadows, appear to be of order kilometers or so in size. One thing that a spacecraft can do that we can't do from Earth, and that is fly into Saturn's shadow and look at Saturn from the night side. So this is with the sun back illuminating the planet. So the sun is shining through the rings from the opposite side, and that allows us to see how light is scattered. That gives us information about what sort of size distribution we've got of the individual particles in the rings, as well as how they're moving. So that is simply something that is simply not possible from Earth, because we're always looking at the planets from the sunlit side when we're looking at the outer solar system. One of the stowaways, well, no, not a stowaway, it's part of the mission. Huygens is a little spacecraft that hitched a ride on Cassini and was released shortly after arrival at the planet in order to explore the moon Titan. It was released and then parachuted into Titan. Remember, Titan's got a rather thick atmosphere, so we don't have to do any fancy aero braking. It was simply a parachute that brought it down to the surface. But as it came through the atmosphere, the cameras were looking down, recording its fall through the atmosphere. Up till now, because of a very thick, hazy atmosphere, we didn't really know what the surface of Titan looked like. But Huygens going through the atmosphere, looking down, we now know that Titan actually has mountains, it has lakes, it has rivers, it has clouds, it has rain, just like here. Not quite the same, because most of those clouds and rain are not necessarily water, but it looks like the geological features of this particular moon are much more similar to the rocky planets that we know and love in the inner solar system compared to some of the icy moons in the outer part of the solar system. So this particular lander was a very useful way of getting an idea of what this particular moon looks like. Let's have a quick look at a mission to Jupiter. This is Juno. 2016, a few years after, slightly overlapping, but a few years after the mission we've just described to Saturn. Again, some of the numbers are quite incredible. The number of billion miles launched, terabytes of data taken from both looking at the planet as well as looking at the moons. If we take Jupiter and attempt to sort of unwrap it, that's the familiar view of Jupiter with belts and zones, etc. If we just unwrap it, we can see that there's an awful lot of structure there. Trying to understand the weather system, why do we have different colors? We think that's because of different elements, some of which are being churned up from different depths, different levels of the Jupiter atmosphere. They're also traveling in different directions, understanding why it is that some winds seem to blow from east to west and some seem to blow from west to east, causing storm systems such as the Great Red Spot there. But Juno, the mission, has enabled us to get much higher resolution images than we could possibly get from Earth. This is a flyby of Jupiter's pole. Juno spends most of its time away from Jupiter because of the radiation and swoops in every once in a while. Every few months it swoops in. This is a time lapse taken over a few hours, and you can see incredible detail in the storm systems as it swoops. There's lightning. Those flashes of white there you can see are lightning flashes that it's seeing in the storm system. Over a few hours it swoops past the planet and again gives us high resolution images of the atmosphere, and it's doing this time and time again. Every few months it's swooping down, sweeping over a different part of the planet, trying to understand how it's put together, why we're getting particular structures in the poles, and understanding what the various colors are telling us about the chemistry of what elements exist in Jupiter's atmosphere. There's just a single static shot, which just reminds you that one image alone, in principle, the analysis of this could take years to try and understand how these storm systems are developing with the different winds in different directions, why we get these white spots, what makes storm systems so persistent on Jupiter, whereas they seem to die on other planets. This is another snapshot taken when the spacecraft was only perhaps tens of kilometers or so above the cloud tops of Jupiter. It is thought that apart from the fact this looks like an impressionist painting of or watercolor left out in the rain or something like that, it is thought that this dark spot in the middle is perhaps a vortex. It is perhaps what we're doing is looking down into deeper parts of Jupiter, and the colors that we can see there are the result of different elements, different materials, different compounds being churned up, and perhaps we've got a little peek into much deeper layers there. This is just a short video to remind us just how complex a storm system can be, or at least just the cloud tops. This is a sort of artificially colored video showing us just what is going on. And if you think trying to predict the weather on Earth is bad enough, trying to predict what is going on with a system like this with very high-speed winds churning the atmosphere in different directions, again, that's what a number of people are trying to do there. Let's remind ourselves that the solar system is not just the Sun and the 8 planets and a few dwarf planets as well. New Horizons, for instance, was sent out to explore Pluto, and like most of these missions, it didn't go into orbit, it just flew past and kept going. So New Horizons, like Voyager, like Pioneer, are leaving our solar system. The question is, what does it do on the way out? As it leaves the orbit of Pluto, it's going to be flying through the Kuiper Belt. There might be other interesting objects out there which are worth closer inspection. Even apart from that, if we stay closer to home, there are still 300 moons in our solar system. Okay, Jupiter and Saturn have got most of them, and the rest of the planets have got a smattering between them, but that's still 300 worlds in their own right that might be worth exploring. So there's just a handful of them. Some we can see, like our familiar moon of Earth. Some of them look more like the Star Wars Death Star compared to anything else. That's a big Herschel crater on the moon Mimas. And large ones tend to be more spherical. Small ones tend to be a little more potato-shaped. If we have a look at the large ones that are relatively spherical, here's the major moons of the solar system. There's the huge Titan with its rather fuzzy atmosphere, stopping us from seeing any surface detail. Hence the need to send Huygens in as a probe to see what the surface actually looks like. A number of these are very interesting. Io itself is a volcanic world, but interest lately has focused not around Io, one of the 4 Galilean moons of Jupiter, but the other 3, Europa, Ganymede, and Callisto. These are the so-called icy moons of Jupiter, because it looks like there's an awful lot of water on these worlds. that we can infer from previous measurements. There is more water on these moons than there is in all of the Atlantic and the Pacific Oceans. So we know life developed here, and we are pretty sure life developed in our oceans. So if there are oceans of water, usually underneath an ice crust in this case, on these icy moons, then is it not possible that life has also evolved on these worlds? Which is why we've sent exploratory ships out. ESA has sent the mission JUICE more than a year ago, Jupiter's icy moons, and NASA have sent Europa Clipper on its way to Europa to get a closer look at these worlds to try and understand whether or not life does exist in these worlds. If you've got water, if you've got the right elements, and you've got an energy source, those are the three things you need for life to evolve. It looks like those icy moons have all of the ingredients they need for life to evolve. Some people think if that's the case, life is inevitable. Other people think it's less likely. We don't know until we go visit and find out. These missions that are going to the outer parts of the solar system, how are we sending these commands out? How are we getting the information back? How are we getting these images back? Well, usually it's done with a large radio dish. There's a Cassini again, there's Huygens on the side. A large radio dish on the spacecraft will send a radio signal back to Earth, and it'll be picked up by an enormous radio dish on Earth. That's how it's been done for the last half century. But there are now tests being done. For instance, the last mission to Psyche, which is a small asteroid, the mission not only had the standard radio communication, they thought they would do a test just to see if there's a better way of getting the data back. And so it's thought, wouldn't lasers be better? Lasers are lower powered and in principle can have much higher data rates. Those of you who've got broadband might realize that an optical fiber to your house allows you to get data squeezed down the optical fiber much faster than any other means. And in principle, you should be able to send signals down a laser thousands of times faster than you can send them on the back of a radio beam. So they thought, let's give it a test. Let's send a signal from this Psyche probe, and let's see just how fast we can get the data down again. Let's not send an image, that's too easy. Images are too small. Let's send something a little more challenging. Let's send a high definition video, effectively Netflix times 10 or something, down the laser beam. So what are we going to choose as the video to send on our laser? Somebody at NASA figured the best test for a video laser transmission is a video of a cat chasing a laser beam. So there's a cat chasing a laser. And it was sent from the asteroid Psyche. And what they found was at a distance of 50 million kilometers, they could get a download speed of 260 megabits per second. That's faster than some people can get on their broadband being sent from 10 miles away. But this is at a distance of 50 million kilometers. Even at a distance of 400 million kilometers on the other side of the solar system, they could still get 8 megabits per second, more than fast enough to stream Netflix a few times over. So these data rates are much higher than we can get with radio signals. So perhaps in the future, we won't be limited to just having a few images coming back from our spacecraft. Maybe we'll actually have enough data rate to get high definition videos coming back virtually streamed live, rather than let's wait a few months and eventually we'll get all the data back from this spacecraft. So there's a lot going on out there. The Cassini mission has now finished. Cassini is dead, it's been crashed into Saturn. But Bepi Colombo is on its way, using gravity assist to get to Mercury. It should be in orbit before too long. New Horizons is on its way out of the solar system. Juno is still exploring Jupiter and is coming to the end of its life. And as I've just said, we've got two new missions that are now on their way to explore the icy moons of Jupiter. We've got the ESA mission and the NASA mission. We've got JUICE, Jupiter's icy moons, and we've got Europa Clipper. So if you want to know more about any of these past missions and any of the missions that are currently en route and any missions that are being planned, have a look at these various websites, and you will find more information about what we as a humankind are doing to explore our solar system. Thank you very much.